Ray optics and optical instruments. Nature has endowed the human eye, that is retina, with the sensitivity to detect electromagnetic waves within a small range of the electromagnetic spectrum. Electromagnetic radiation belonging to this region of the spectrum, which wavelength of about 400 nanometer to 750 nanometer, is called light. It is mainly through light and the sense of vision that we know and interprets the world around us. There are two things about light. One, that it travels with enormous speed, and two, that it travels in a straight line. The speed of light is finite and measurable. Its accepted value in a vacuum is c is equal to 2.99792458 into 10 raised to 8 meter per second. For many purposes, it suffices to take c is equal to 3 into 10 raised to 8 meter per second. The speed of light in a vacuum is the highest speed attainable in nature. The intuitive notion that light travels in a straight line seems to contradict that light is an electromagnetic wave of wavelength belonging to the visible part of the spectrum. How to reconcile the two facts? The answer is that the wavelength of light is very small compared to the size of ordinary objects that we encounter commonly, that is, generally of the order of a few centimeters or larger. A light wave can be considered to travel from one point to another along a straight line joining them. The path is called a ray of light, and a bundle of such rays constitutes a beam of light. In this chapter, we consider the phenomena of reflection, refraction, and dispersion of light. Using the ray picture of light, using the basic laws of reflection and refraction, we shall study the image formation by plane and spherical reflecting and refracting surfaces. We then go on to describe the construction and working of some important optical instruments, including the human eye. Reflection of light by spherical mirrors. The angle of reflection, that is, the angle between the reflected ray and the normal to the reflecting surface or the mirror, equals the angle of incidence. The angle between the incident ray and the normal. Also that the incident ray, reflected ray and the normal to the reflecting surface at the point of incidence lie in the same plane. These laws are valid at each point on any reflecting surface, whether plane or curved. However, we shall restrict our discussion to the special case of curved surfaces, that is, spherical surfaces. The normal in this case is to be taken as normal to the tangent to the surface at the point of incidence. That is, the normal is along the radius, the line joining the center of curvature of the mirror to the point of incidence. We have already studied that the geometric center of a spherical mirror is called its pole P, while that of a spherical lens is called its optical center. The line joining the pole P and the center C of curvature of the spherical mirror is known as the principal axis. In the case of spherical lenses, the principal axis is the line joining the optical center with its principal focus. Sign convention. To derive the relevant formulae for reflection by spherical mirrors and refraction by spherical lenses, we must first adopt a sign convention for measuring distances. According to sign convention, all distances are measured from the pole P of the mirror or the optical center of the lens. The distances measured in the same direction as the incident light are taken as positive, and those measured in the direction opposite to the direction of the incident light are taken as negative. The heights measured upwards with respect to the x-axis and normal to the principal axis, that is x-axis of the mirror or lens, are taken as positive. The heights measured downwards are taken as negative. With a commonly accepted convention, it turns out that a single formula for spherical mirrors and a single formula for spherical lenses can handle all different cases. Focal length of spherical mirrors. The figure shows what happens when a parallel beam of light is incident on A, a concave mirror, and B, a convex mirror. We assume that the rays are paraxial, that is, they are incident at points close to the pole P of the mirror and make small angles with the principal axis. The reflected rays converge at point F on the principal axis of a concave mirror. For a convex mirror, the reflected rays appear to diverge from point F on its principal axis. Point F is called the principal focus of the mirror. If the parallel paraxial beam of light were incident, making some angle with the principal axis, the reflected rays would converge or appear to diverge from a point in a plane through F normal to the principal axis. This is called the focal plane of the mirror. The distance between the focus F and the pole P of the mirror is called the focal length of the mirror, denoted by F. We now show that F is equal to R upon 2, where R is the radius of curvature of the mirror. The geometry of the reflection of an incident ray is shown in figure. Let C be the center of curvature of the mirror. Consider a ray parallel to the principal axis striking the mirror at M. Then CM will be perpendicular to the mirror at M. Let theta be the angle of incidence and MD be the perpendicular from M on the principal axis. Then angle MCP is equal to theta and angle MFP is equal to 2 theta. Now tan theta is equal to MD upon CD and tan 2 theta is equal to MD upon FD. Equation 1. For small theta, which is true for paraxial rays, tan theta is approximately equal to theta. Tan 2 theta is approximately equal to 2 theta. Therefore, equation 1 gives MD upon FD is equal to 2 MD upon CD, or FD is equal to CD upon 2, equation 2. Now, for small theta, the point D is very close to the point P. Therefore, FD is equal to F and CD is equal to R. Equation 2 then gives F is equal to R upon 2. Equation 3. The mirror equation. If rays emanating from a point actually meet another point after reflection and or refraction, that point is called the image of the first point. The image is real if the rays actually converge to the point. It is virtual if the rays do not actually meet but appear to diverge from the point when produced backwards. An image is thus a point-to-point corresponds with the object established through reflection and or refraction. In principle, we can take any two rays emanating from a point on an object, trace their paths, find their point of intersection and thus obtain the image of the point due to reflection at a spherical mirror. It is convenient to choose any two of the following rays. Number 1. The ray from the point which is parallel to the principal axis. The reflected ray goes through the focus of the mirror. Number 2. The ray passing through the center of curvature of a concave mirror or appearing to pass through it for a convex mirror. The reflected ray simply retraces the path. Number 3. The ray passing through or directed towards the focus of the concave mirror or appearing to pass through or directed towards the focus of a convex mirror. The reflected ray is parallel to the principal axis. Number 4. The ray incident at any angle at the pole P. The reflected ray follows laws of reflection. Figure shows the ray diagram considering 3 rays. It shows the image A', B', in this case real, of an object AB formed by a concave mirror, an infinite number of rays emanating from any source in all directions. Thus, point A' is the image point of A if every ray originating at point A and falling on the concave mirror after reflection passes through point A'. We now derive the mirror equation or the relation between the object distance u, image distance v, and the focal length f. From figure, the two right-angled triangles A', B', F and MPF are similar. For paraxial rays, MP can be considered to be a straight line perpendicular to CP. Therefore, B', A' upon PM is equal to B', F upon FP, or B', A' upon BA is equal to B', F upon FP, because PM is equal to BA. Equation 4. Since angle APB is equal to angle A'P', the right-angled triangles A'B', and ABP are also similar. Therefore, B', A' upon BA is equal to B', upon BP. Equation 5. Comparing equations 4 and 5, we get B', F upon FP is equal to B', minus FP upon FP is equal to B', upon BP. Equation 6. Equation 6 is a relation involving the magnitude of distances. Light travels from the object to the mirror MPN. Hence, this is taken in a positive direction. To reach object AB, image A', B', as well as the focus F from pole P, we have to travel opposite to the direction of incident light. Hence, all three will have negative signs. Thus, B', is equal to minus V, FP is equal to minus F, BP is equal to minus U. Using this in equation 6, we get minus V plus F upon minus F is equal to minus V upon minus U, or V minus F upon F is equal to V upon U. V upon F is equal to 1 plus V upon U. Dividing it by V, we get 1 upon V plus 1 upon U is equal to 1 upon F. Equation 7. This relation is known as the mirror equation. The size of the image relative to the size of the object is another important quantity to consider. Linear magnification M as the ratio of the height of the image H' to the height of the object H. M is equal to H' upon H. Equation 8. H and H' will be taken positive or negative in accordance with the accepted sign convention. In triangles A', B', P and ABP, we have B', A' upon BA is equal to B', P upon BP, minus H' upon H is equal to minus V upon minus U. So that M is equal to minus H' upon H is equal to minus V upon U. Equation 9. We have derived here the mirror equation, equation 7, and the magnification formula, equation 9, for the case of real inverted image formed by a concave mirror with the proper use of sign convention. These are, in fact, valid for all the cases of reflection by a spherical mirror, that is concave or convex, whether the image formed is real or virtual. Figure shows the ray diagrams for virtual image formed by a concave and convex mirror. You should verify that equations 7 and 9 are valid for these cases as well. Example 1. Suppose that the lower half of the concave mirror's reflecting surface in figure is covered with an opaque, that is non-reflective material. What effect will this have on the image of an object placed in front of the mirror? Solution. You may think that the image will now show only half of the object. But taking the laws of reflection to be true for all points of the remaining part of the mirror, the image will be that of the whole object. However, as the area of the reflecting surface has been reduced, the intensity of the image will be low, in this case half. Example 2. A mobile phone lies along the principal axis of a concave mirror as shown in figure. Show by the suitable diagram the formation of its image. Explain why the magnification is not uniform. Will the distortion of the image depend on the location of the phone with respect to the mirror? Solution. The ray diagram for the formation of the image of the phone is shown in figure. The image of the part which is on the plane perpendicular to the principal axis will be on the same plane. It will be of the same size, that is BC is equal to BC. You can yourself realize why the image is distorted. Example 3. An object is placed at 1 10 cm, 2 5 cm in front of a concave mirror of radius of curvature 15 cm. Find the position, nature and magnification of the image in each case. Solution. The focal length f is equal to minus 15 upon 2 is equal to minus 7.5 cm. Number 1. The object distance u is equal to minus 10 cm. Then equation 7 gives 1 upon v plus 1 upon u is equal to 1 upon f. 1 upon v plus 1 upon minus 10 is equal to 1 upon minus 7.5 is equal to 10 into 7.5 upon minus 2.5 is equal to minus 30 cm. The image is 30 cm from the mirror on the same side as the object. Also magnification m is equal to minus v upon minus u is equal to minus 30 upon minus 10 is equal to minus 3. The image is magnified, real and inverted. Number 2. The object distance u is equal to minus 5 cm. Then from equation 7, 1 upon v plus 1 upon u is equal to 1 upon f. 1 upon v plus 1 upon minus 5 is equal to 1 upon minus 7.5. V is equal to 5 into 7.5 upon 7.5 minus 5 is equal to 15 cm. This image is formed at 15 cm behind the mirror. It is a virtual image. Magnification m is equal to minus v upon u is equal to minus 15 upon minus 5 is equal to 3. The image is magnified, virtual and erect. Example 4. Suppose while sitting in a parked car, you notice a jogger approaching towards you in the side view mirror of r is equal to 2 meter. If the jogger is running at a speed of 5 meter per second, how fast the image of the jogger appear to move when the jogger is A. 39 meter, B. 29 meter, C. 19 meter and D. 9 meter away. Solution. From the mirror equation, equation 7, V is equal to Fu upon U minus F. For convex mirror, since R is equal to 2 meter, F is equal to 1 meter, A. Then for U is equal to minus 39 meter, V is equal to minus 39 into 1 upon minus 39 minus 1 is equal to 39 upon 40 meter. Since the jogger moves at a constant speed of 5 meter per second, after 1 second, the position of the image V for U is equal to minus 39 plus 5 is equal to minus 34 is 34 upon 35 meter. The shift in the position of image in 1 second is 39 upon 40 minus 34 upon 35 is equal to 1365 minus 1360 upon 1400 is equal to 1 upon 280 meter. Therefore, the average speed of the image when the jogger is between 39 meter and 34 meter from the mirror is 1 upon 280 meter per second. Similarly, it can be seen that for U is equal to minus 29 meter, minus 19 meter and minus 9 meter, the speed with which the image appears to move is 1 upon 150 meter per second, 1 upon 60 meter per second and 1 upon 10 meter per second respectively. Although the jogger has been moving at a constant speed, the speed of his or her image appears to increase substantially as he or she moves closer to the mirror. This phenomenon can be noticed by any person sitting in a stationary car or a bus. In the case of moving vehicles, a similar phenomenon could be observed if the vehicle in the rear is moving closer with a constant speed. Refraction. When a beam of light encounters another transparent medium, a part of the light gets reflected back into the first medium while the rest enters the other. A ray of light represents a beam. The direction of propagation of an obliquely incident, that is 0 degree less than I less than 90 degree, ray of light that enters the other medium changes at the interface of the two media. This phenomenon is called refraction of light. Snell experimentally obtained the following laws of refraction. Number 1. The incident ray, the reflected ray, and the normal to the interface at the point of incidence all lie in the same plane. Number 2. The ratio of the sine of the angle of incidence to the sine of angle of refraction is constant. The angles of incidence I and refraction R are the angles that the incident and its refracted ray make with the normal respectively. We have sin I upon sin R is equal to n to 1, equation 10, where n to 1 is a constant called the refractive index of the second medium with respect to the first medium. Equation 10 is the well-known Snell's law of refraction. N to 1 is a characteristic of the pair of media and also depends on the wavelength of light, but is independent of the angle of incidence. From equation 10, if n to 1 is greater than 1, R is less than I, that is, the refracted ray bends towards the normal. In such a case, medium 2 is said to be optically denser, or denser in short, than medium 1. On the other hand, if n to 1 is less than 1, R is greater than I, the refracted ray bends away from the normal. This is the case when incident ray in a denser medium refracts into a rarer medium. If N21 is the refractive index of medium 2 with respect to medium 1 and N12 the refractive index of medium 1 with respect to medium 2. N12 is equal to 1 upon N21, equation 11. If N23 is the refractive index of medium 3 with respect to medium 2, then N32 is equal to N31 into N12, where N31 is the refractive index of medium 3 with respect to medium 1. For a rectangular slab, refraction takes place at two interfaces, which is air glass and glass air. It is easily seen from figure that R2 is equal to I1, that is, the emergent ray is parallel to the incident ray. There is no deviation, but it does suffer lateral displacement or shift with respect to the incident ray. Another observation is that the bottom of a tank filled with water appears to be raised. For viewing near the normal direction, it can be shown that the apparent depth h1 is the real depth h2 divided by the refractive index of the medium, that is water. The refraction of light through the atmosphere is responsible for many interesting phenomena. For example, the sun is visible a little before the actual sunrise and until a little after the actual sunset due to the refraction of light through the atmosphere. By actual sunrise, we mean the actual crossing of the horizon by the sun. The refractive index of air with respect to vacuum is 1.00029. Due to this, the apparent shift in the direction of the sun is by about half a degree and the corresponding time difference between actual sunset and apparent sunset is about 2 minutes. The apparent flattening, that is oval shape, of the sun at sunset and sunrise is also due to the same phenomenon. Example 5. The earth takes 24 hours to rotate once about its axis. How much time does the sun take to shift by 1 degree when viewed from the earth? Solution. Time taken for 360-degree shift is equal to 24 hours. Time taken for 1 degree shift is equal to 24 upon 360 hour is equal to 4 minutes. Total internal reflection. When light travels from an optically denser medium to a rarer medium, at the interface, it is partly reflected back into the same medium and partly reflected to the second medium. This reflection is called the internal reflection. When a ray of light enters from a denser medium to a rarer medium, it bends away from the normal. For example, the ray AO1B in figure. The incident ray AO1 is partially reflected O1C and partially transmitted O1B or refracted. The angle of refraction R being larger than the angle of incidence I. As the angle of incidence increases, so does the angle of refraction till for the ray AO3. The angle of refraction is pi by 2. The refracted ray is bent so much away from the normal that it grazes the surface at the interface between the two media. This is shown by the ray AO3D in figure. If the angle of incidence is increased still further, for example, the ray AO4, refraction is not possible and the incident ray is totally reflected. This is called total internal reflection. When light gets reflected by a surface, normally some fraction of it gets transmitted. The reflected ray, therefore, is always less intense than the incident ray. Howsoever smooth the reflecting surface may be, in total internal reflection, on the other hand, no transmission of light takes place. The angle of incidence corresponding to an angle of refraction 90 degree, say angle AO3N, is called the critical angle IC for the given pair of media. We see from Snell's law that if the relative refractive index is less than 1, then, since the maximum value of sin R is unity, there is an upper limit to the value of sin I, for which the law can be satisfied, that is I is equal to IC, such that sin IC is equal to n to 1, equation 12. For values of I larger than IC, Snell's law of refraction cannot be satisfied and hence no refraction is possible. The refractive index of denser medium 1 with respect to rarer medium 2 will be N12 is equal to 1 upon sin IC. Some typical critical angles are listed in table. Critical angle of some transparent media. Substance medium, refractive index, critical angle. Water 1.33, 48.75 degree. Chrome glass 1.52, 41.14 degree. Dense flint glass 1.62, 37.31 degree. Diamond 2.42, 24.41 degree. A demonstration for total internal reflection. All optical phenomena can be demonstrated very easily with the use of a laser torch or pointer. Take a glass beaker with clear water in it. Add a few drops of milk or any other suspension to the water and stir so that water becomes a little turbid. Take a laser pointer and shine its beam through the turbid water. You will find that the path of the beam inside the water shines brightly. Shine the beam from below the beaker such that it strikes the upper water surface at the other end. Do you find that it undergoes partial reflection and partial refraction? Now direct the laser beam from one side of the beaker such that it strikes the upper surface of water more obliquely. Adjust the direction of the laser beam until you find the angle for which the refraction above the water surface is totally absent and the beam is totally reflected back to the water. This is a total internal reflection at its simplest. Pour this water into a long test tube and shine the laser light from the top as shown in figure. Adjust the direction of the laser beam such that it is totally internally reflected every time it strikes the walls of the tube. This is similar to what happens in optical fibers. Total internal reflection in nature and its technological applications. Number 1. Mirage. On hot summer days, the air near the ground becomes hotter than the air at higher levels. The refractive index of air increases with its density. Hotter air is less dense and has a smaller refractive index than cooler air. If the air currents are small, that is, the air is still, and the optical density at different layers of air increases with height. As a result, light from a tall object, such as a tree, passes through a medium whose refractive index decreases towards the ground. Thus, a ray of light from such an object successively bends away from the normal and undergoes total internal reflection if the angle of incidence for the air near the ground exceeds the critical angle. This is shown in figure. To a distance observer, the light appears to be coming from somewhere below the ground. The observer naturally assumes that light is being reflected from the ground, say by a pool of water near the tall object. Such inverted images of distant tall objects cause an optical illusion to the observer. This phenomenon is called mirage. This type of mirage is especially common in hot deserts. Some of you might have noticed that while moving in a bus or a car during a hot summer day, a distant patch of road, especially on a highway, appears to be wet, but you do not find any evidence of wetness when you reach that spot. This is also due to mirage. Number 2. Diamond. Diamonds are known for their spectacular brilliance. Their brilliance is mainly due to the total internal reflection of light inside them. The critical angle for the diamond-air interface is approximately equal to 24.4 degree is very small. Therefore, once light enters a diamond, it is very likely to undergo total internal reflection inside it. Diamonds found in nature rarely exhibit the brilliance for which they are known. It is the technical skill of a diamond cutter that make diamonds sparkle so brilliantly. Number 3. Prism. Prisms designed to bend light by 90 degree or by 180 degree make use of total internal reflection. Such a prism is also used to invert images without changing their size. In the first two cases, the critical angle IC for the material of the prism must be less than 45 degree. We see from table that this is true for both crown glass and dense flint glass. Number 4. Optical fibers. Optical fibers are extensively used for transmitting audio and video signals through long distances. Optical fibers to make use of the phenomenon of total internal reflection. Optical fibers are fabricated with high-quality composite glass or quartz fibers. Each fiber consists of a core and cladding. The refractive index of the material of the core is higher than that of the cladding. When a signal in the form of light is directed at one end of the fiber at a suitable angle, it undergoes repeated total internal reflections along the length of the fiber and finally comes out at the other. Optical fibers are fabricated such that light reflected at one side of the inner surface strikes the other at an angle larger than the critical angle. Even if the fiber is bent, light can easily travel along its length. Thus, an optical fiber can be used to act as an optical pipe. A bundle of optical fibers can be put to several uses. Optical fibers are extensively used for transmitting and receiving electrical signals which are converted to light by suitable transducers. Obviously, optical fibers can also be used for the transmission of optical signals. For example, these are used as a light pipe to facilitate visual examination of internal organs like the esophagus, stomach, and intestines. You might have seen a commonly available decorative lamp with fine plastic fibers with their free ends forming a fountain-like structure. The other end of the fibers is fixed over an electric lamp. When the lamp is switched on, the light travels from the bottom of each fiber and appears at the tip of its free end as a dot of light. The fibers in such decorative lamps are optical fibers. The main requirement in fabricating optical fibers is that there should be very little absorption of light as it travels for long distances inside them. This has been achieved by purification and special preparation of materials such as quartz. In silica glass fibers, it is possible to transmit more than 95% of the light over a fiber length of 1 kilometer. Refraction at spherical surfaces and by lenses. We have so far considered refraction at a plane interface. We shall now consider refraction at a spherical interface between two transparent media. An infinitesimal part of a spherical surface can be regarded as planar, and the same laws of refraction can be applied at every point on the surface. Just as for reflection by a spherical mirror, the normal at the point of incidence is perpendicular to the tangent plane to the spherical surface at that point and therefore passes through its center of curvature. We first consider refraction by a single spherical surface and follow it by thin lenses. A thin lens is a transparent optical medium bounded by two surfaces, at least one of which should be spherical. Applying the formula for image formation by a single spherical surface successively at the two surfaces of a lens, we shall obtain the lens maker's formula and then the lens formula. Refraction at a spherical surface. Figure shows the geometry of formation of image I of an object O on the principal axis of a spherical surface with center of curvature C and radius of curvature R. The rays are incident from a medium of refractive index N1 to another of refractive index N2. As before, we take the aperture of the surface to be small compared to other distances involved so that small angle approximation can be made. In particular, Nm will be taken to be nearly equal to the length of the perpendicular from the point N on the principal axis. We have four small angles. Tan angle NOM is equal to Mn upon OM. Tan angle NCM is equal to Mn upon MC. Tan angle NIM is equal to Mn upon Mi. Now, for triangle NOC, I is the exterior angle. Therefore, I is equal to angle NOM plus angle NCM. Therefore, I is equal to Mn upon OM plus Mn upon MC. Equation 13. Similarly, R is equal to angle NCM minus angle NIM. That is, R is equal to Mn upon MC minus Mn upon Mi. Equation 14. Now, by Snell's law, N1 sin I is equal to N2 sin R, or for small angles, N1I is equal to N2R. Substituting I and R from equations 13 and 14, we get N1 upon OM plus N2 upon Mi is equal to N2 minus N1 upon MC. Equation 15. Here, OM, Mi and MC represent magnitudes of distances. Applying the Cartesian sign convention, OM is equal to minus U, Mi is equal to plus V, MC is equal to plus R. Substituting this in equation 15, we get N1 upon minus U plus N2 upon V is equal to N2 minus N1 upon R, or N2 upon V minus N1 upon U is equal to N2 minus N1 upon R. Equation 16. Equation 16 gives us a relation between object and image distance in terms of refractive index of the medium and the radius of curvature of the curved spherical surface. It holds for any curved spherical surface. Example 6. Light from a point source in air falls on a spherical glass surface where n is equal to 1.5 and radius of curvature is equal to 20 cm, the distance of the light source from the glass surface is 100 cm. At what position the image is formed? Solution. We use the relation given by equation 16. Here, u is equal to minus 100 cm, v is equal to determine n1 is equal to 1 and n2 is equal to 1.5, r is equal to plus 20 cm. 1.5 upon v plus 1 upon 100 is equal to 0.5 upon 20. Therefore, v is equal to 100 cm. The image is formed at a distance of 100 cm from the glass surface in the direction of incident light. Refraction by a lens. Figure shows the geometry of image formation by a double convex lens. The image formation can be seen in terms of two steps. Number 1. The first refracting surface forms the image I1 of the object O. The image I1 acts as a virtual object for the second surface that forms the image at I. Applying equation 15 to the first interface ABC, we get n1 upon OB plus n2 upon BI1 is equal to n2 minus n1 upon BC1. Equation 17. A similar procedure applied to the second interface ADC gives minus n2 upon di1 plus n1 upon di is equal to n2 minus n1 upon dc2. Equation 18. For a thin lens, bi1 is equal to di1. Adding equation 17 and 18, we get n1 upon ob plus n1 upon di is equal to n2 minus n1 into 1 upon bc1 plus 1 upon dc2. Equation 19. Suppose the object is at infinity, that is, OB tends to infinity and di is equal to f. Equation 19 gives n1 upon f is equal to n2 minus n1 into 1 upon bc1 plus 1 upon dc2. Equation 20. The point where image of an object placed at infinity is formed is called the focus f of the lens, and the distance f gives its focal length. A lens has two foci, f and f' on either side of it. By the sign convention, dc1 is equal to plus r1, dc2 is equal to minus r2. So equation 20 can be written as 1 upon f is equal to n2 1 minus 1 into 1 upon r1 minus 1 upon r2. Because n2 1 is equal to n2 upon n1. Equation 21. Equation 21 is known as the lens maker's formula. It is useful to design lenses of desired focal length using surfaces of suitable radii of curvature. Note that the formula is true for a concave lens also. In that case, R1 is negative, R2 positive, and therefore F is negative. From equations 19 and 20, we get N1 upon OB plus N1 upon DI is equal to N1 upon F. Equation 22. Again, in the thin lens approximation, B and D are both close to the optical center of the lens. Applying the sign convention, BO is equal to minus U, DI is equal to plus V, we get 1 upon V minus 1 upon U is equal to 1 upon F. Equation 23. Equation 23 is the familiar thin lens formula. The formula is valid for both convex as well as concave lenses and for both real and virtual images. The two foci f and f' of a double convex or concave lens are equidistant from the optical center. The focus on the side of the original source of light is called the first focal point, whereas the other is called the second focal point. To find the image of an object by a lens, we can, in principle, take any two rays emanating from a point on an object, trace their paths using the laws of refraction and find the point where the refracted rays meet or appear to meet. However, it is convenient to choose any two of the following rays. Number 1. A ray emanating from the object parallel to the principal axis of the lens after refraction passes through the second principal focus f' in a convex lens or appears to diverge in a concave lens from the first principal focus f. Number 2. A ray of light passing through the optical center of the lens emerges without any deviation after refraction. Number 3. A ray of light passing through the first principal focus for a convex lens or appearing to meet at it for a concave lens emerges parallel to the principal axis after refraction. Figures A and B illustrate these rules for a convex and a concave lens respectively. You should practice drawing similar ray diagrams for different positions of the object with respect to the lens and also verify that the lens formula equation 23 holds good for all cases. Here again, it must be remembered that each point on an object gives out infinite number of rays. All these rays will pass through the same image point after refraction at the lens. Magnification M produced by a lens is defined like that for a mirror, as the ratio of the size of the image to that of the object. Proceeding in the same way as for spherical mirrors, it is easily seen that for a lens, M is equal to H dash upon H is equal to V upon U, equation 24. For erect and virtual image formed by a convex or concave lens, M is positive, while for an inverted and real image, M is negative. Example 7. A magician during a show makes a glass lens with N is equal to 1.47 disappear in a through of liquid. What is the refractive index of the liquid? Could the liquid be water? Solution. The refractive index of the liquid must be equal to 1.47 in order to make the lens disappear. This means N1 is equal to N2. This gives 1 upon F is equal to 0 or F tends to infinity. The lens in the liquid will act like a plain sheet of glass. No, the liquid is not water. It could be glycerine. Power of a lens. Power of a lens is a measure of the convergence of divergence, which a lens introduces in the light falling on it. A lens of shorter focal length bends the incident light more, while converging it in case of a convex lens and diverging it in case of a concave lens. The power P of a lens is defined as the tangent of the angle by which it converges or diverges a beam of light falling at unit distance from the optical center. Tan delta is equal to H upon F. If H is equal to 1, tan delta is equal to 1 upon F, or delta is equal to 1 upon F for small value of delta. Thus, P is equal to 1 upon F, equation 25. The SI unit for power of a lens is diopter. 1 diopter is equal to 1 meter inverse. The power of a lens of focal length of 1 meter is 1 diopter. Power of a lens is positive for a converging lens and negative for a diverging lens. Thus, when an optician prescribes a corrective lens of power plus 2.5 diopter, The required lens is a convex lens of focal length plus 40 cm, a lens of power of minus 4.0 diopter means a concave lens of focal length minus 25 cm. Example 8. 1. If f is equal to 0.5 meter for a glass lens, what is the power of the lens? 2. The radii of curvature of the faces of a double convex lens are 10 cm and 15 cm. Its focal length is 12 cm. What is the refractive index of glass? 3. A convex lens has 20 cm focal length in air. What is focal length in water? Where refractive index of air water is equal to 1.33. Refractive index for air glass is equal to 1.5. Solution. Number 1. Power is equal to plus 2 diopter. Number 2. Here we have f is equal to plus 12 cm, r1 is equal to plus 10 cm, r2 is equal to minus 15 cm. Refractive index of air is taken as unity. We use the lens formula of equation 22. The sign convention has to be applied for f, r1 and r2. Substituting the values, we have 1 upon 12 is equal to n minus 1 into 1 upon 10 minus 1 upon minus 15. This gives n is equal to 1.5. Number 3. For a glass lens in air, n2 is equal to 1.5, n1 is equal to 1, f is equal to plus 20 cm. Hence, the lens formula gives 1 upon 20 is equal to 0.5 into 1 upon r1 minus 1 upon r2. For the same glass lens in water, n2 is equal to 1.5, n1 is equal to 1.33. 1.33 upon f is equal to 1.5 minus 1.33 into 1 upon r1 minus 1 upon r2. Equation 26. Combining these two equations, we find f is equal to plus 78.2 cm. Combination of thin lenses in contact. Consider two lenses A and B of focal length f1 and f2 placed in contact with each other. Let the object be placed at a point O beyond the focus of the first lens A. The first lens produces an image at I1. Since image I1 is real, it serves as a virtual object for the second lens P, producing the final image at I. Formation of image by the first lens is presumed only to facilitate determination of the position of the final image. In fact, the direction of rays emerging from the first lens gets modified in accordance with the angle at which they strike the second lens. Since the lenses are thin, we assume the optical centers of the lenses to be coincident. Let this central point be denoted by P. For the image formed by the first lens A, we get 1 upon V1 minus 1 upon U is equal to 1 upon F1. Equation 27. For the image formed by the second lens B, we get 1 upon V minus 1 upon V1 is equal to 1 upon F2. Equation 28. Adding equation 27 and 28, we get 1 upon V minus 1 upon U is equal to 1 upon F1 plus 1 upon F2. Equation 29. If the two-lens system is regarded as equivalent to a single lens of focal length f, we have 1 upon V minus 1 upon U is equal to 1 upon F. 1 upon F is equal to 1 upon F1 plus 1 upon F2. Equation 30. The derivation is valid for any number of thin lenses in contact. If several thin lenses of focal length f1, f2, f3 up to so on are in contact, the effective focal length of their combination is given by 1 upon f is equal to 1 upon f1 plus 1 upon f2 plus 1 upon f3 plus up to so on. Equation 31. In terms of power, equation 31 can be written as P is equal to P1 plus P2 plus P3 plus up to so on. Equation 32, where P is the net power of the lens combination. Note that the sum in equation 32 is an algebraic sum of individual powers, so sum of the terms on the right side may be positive for convex lenses and some negative for concave lenses. Combination of lenses helps to obtain diverging or converging lenses of desired magnification. It also enhances sharpness of the image, since the image formed by the first lens becomes the object for the second. Equation 25 implies that the total magnification M of the combination is a product of magnification M1, M2, M3 up to so on of individual lenses. M is equal to M1 into M2 into M3 into up to so on. Equation 33. Such a system of combination of lenses is commonly used in designing lenses for cameras, microscopes, telescopes, and other optical instruments. Example 9. Find the position of the image formed by the lens combination given in the figure. F is equal to plus 10, minus 10, plus 30. Solution. Image formed by the first lens 1 upon V1 minus 1 upon U1 is equal to 1 upon F1. Therefore, 1 upon V1 minus 1 upon minus 30 is equal to 1 upon 10. V1 is equal to 15 cm. The image formed by the first lens serves as the object for the second. This is at a distance of 15 minus 5 cm is equal to 10 cm to the right of the second lens. Though the image is real, it serves as a virtual object for the second lens, which means that the rays appear to come from it for the second lens. 1 upon V2 minus 1 upon 10 is equal to 1 upon minus 10, or V2 is equal to infinity. The virtual image is formed at an infinite distance to the left of the second lens. This acts as an object for the third lens. 1 upon V3 minus 1 upon U3 is equal to 1 upon F3, or 1 upon V3 minus 1 upon infinity is equal to 1 upon 30, or V3 is equal to 30 cm. The final image is formed 30 cm to the right of the third lens. Refraction through a prism. Figure shows the passage of light through a triangular prism ABC. The angles of incidence and refraction at the first face AB are I and R1, while the angle of incidence from glass to air at the second face AC is R2, and the angle of refraction or emergence E. The angle between the emergent ray RS and the direction of the incident ray PQ is called the angle of deviation delta. In the quadrilateral AQ and R, two of the angles at the vertices Q and R are right angles. Therefore, the sum of the other angles of the quadrilateral is 180 degree. Angle A plus angle Q and R is equal to 180 degree. From the triangle Q and R, R1 plus R2 plus angle Q and R is equal to 180 degree. Comparing these two equations, we get R1 plus R2 is equal to A. Equation 34. The total deviation delta is the sum of deviations at the two faces. Delta is equal to I minus R1 plus E minus R2. That is, delta is equal to I plus E minus A. Equation 35. Thus, the angle of deviation depends on the angle of incidence. A plot between the angle of deviation and angle of incidence is shown in figure. You can see that in general, any given value of delta except for I is equal to E corresponds to two values I and hence of E. This, in fact, is expected from the symmetry of I and E. In equation, that is, delta remains the same if I and E are interchanged. Physically, this is related to the fact that the path of ray in figure can be traced back, resulting in the same angle of deviation. At the minimum deviation dm, the refracted ray inside the prism becomes parallel to its base. We have delta is equal to dm, I is equal to E, which implies R1 is equal to R2. Equation 34 gives 2R is equal to A or R is equal to A upon 2. Equation 36. In the same way, equation 35 gives dm is equal to 2I minus A or I is equal to A plus dm upon 2. Equation 37. The refractive index of the prism is N21 is equal to N2 upon N1 is equal to sin A plus dm upon 2 whole upon sin A upon 2. Equation 38. The angles A and dm can be measured experimentally. Equation 38 thus provides a method of determining refractive index of the material of the prism. For a small angle prism, that is a thin prism, dm is also very small, and we get N21 is equal to sin A plus dm upon 2 whole upon sin A upon 2 is approximately equal to A plus dm upon 2 whole upon A upon 2. dm is equal to N21 minus 1 into A. It implies that thin prisms do not deviate light much. Some natural phenomena due to sunlight. The interplay of light with things around us gives rise to several beautiful phenomena. The spectacles of colors that we see around us all the time is possible due to sunlight. Color is associated with the frequency of light or the wavelength of light in the given medium. In the visible spectrum, red light is at the long wavelength end, which is similar to 700 nanometer, while the violet light is at the short wavelength end, which is similar to 400 nanometer. Dispersion takes place because the refractive index of medium for different frequencies for colors is different. For example, the bending of red component of white light is least while it is most for the violet. Equivalently, red light travels faster than violet light in a glass prism. Thick lenses could be assumed as made of many prisms. Therefore, thick lenses show chromatic aberration due to dispersion of light. When white light passes through thick lenses, red and blue colors focus at different points. This phenomenon is known as chromatic aberration. Refractive indices for different wavelengths. Color, wavelength in nanometer, crown glass, flint glass. Violet, 396.9, 1.533, 1.663. Blue, 486.1, 1.523, 1.639. Yellow, 589.3, 1.517, 1.627. Red, 656.3, 1.515, 1.622. The variation of refractive index with wavelength may be more pronounced in some media than the other. In vacuum, of course, the speed of light is independent of wavelength. Thus, vacuum or air approximately is a non-dispersive medium in which all colors travel with the same speed. This also follows from the fact that sunlight reaches us in the form of white light and not as its components. On the other hand, glass is a dispersive medium. The blue of the sky, white clouds, the red hue at sunrise and sunset, the rainbow, the brilliant colors of some pearls, shells, and wings of birds are just a few of the natural wonders we are used to. We describe some of them here from the point of view of physics. The rainbow. The rainbow is an example of the dispersion of sunlight by the water drops in the atmosphere. This is a phenomenon due to combined effect of dispersion, refraction, and reflection of sunlight by spherical water droplets of rain. The conditions for observing a rainbow are that the sun should be shining in one part of the sky while it is raining in the opposite part of the sky. An observer can therefore see a rainbow only when his back is towards the sun. In order to understand the formation of rainbows, consider figure. Sunlight is first refracted as it enters a raindrop, which causes the different wavelengths colors of white light to separate. Longer wavelength of light of red are bent the least while the shorter wavelength of violet are bent the most. Next, these component rays strike the inner surface of the water drop and get internally reflected if the angle between the refracted ray and normal to the drop surface is greater than the critical angle, which is 48 degrees in this case. The reflected light is refracted again when it comes out of the drop, as shown in the figure. It is found that the violet light emerges at an angle of 40 degrees related to the incoming sunlight, and red light emerges at an angle of 42 degrees. For other colors, angles lie in between these two values. Figure explains the formation of primary rainbow, red light from drop 1 and violet light from drop 2 reach the observer's eye. The violet from drop 1 and red light from drop 2 are directed at level above or below the observer. Thus, the observer sees a rainbow with red color on the top and violet on the bottom. The primary rainbow is a result of three-step process, that is, refraction, reflection, and refraction. When light rays undergoes two internal reflections inside a raindrop instead of one as in the primary rainbow, a secondary rainbow is formed as shown in figure. It is due to four-step process. The intensity of light is reduced at the second reflection and hence the secondary rainbow is fainter than the primary rainbow. Further, the order of the colors is reversed in it as is clear from figure. Scattering of light. As sunlight travels through the Earth's atmosphere, it gets scattered, that is, changes its direction by the atmospheric particles. Light of shorter wavelengths is scattered much more than light of longer wavelengths. The amount of scattering is inversely proportional to the fourth power of the wavelength. This is known as Rayleigh scattering. Hence, the bluish color predominates in a clear sky, since blue has a shorter wavelength than red and is scattered much more strongly. In fact, violet gets scattered even more than blue, having a shorter wavelength. But since our eyes are more sensitive to blue than violet, we see the sky blue. Large particles like dust and water droplets present in the atmosphere behave differently. The relevant quantity here is the relative size of the wavelength of light lambda and the scatter of typical size, say A. For A is much less than lambda, one has Rayleigh scattering, which is proportional to 1 upon lambda raised to 4. For A is much greater than lambda, that is large scattering objects, for example, raindrops, large dust or ice particles, this is not true. All wavelengths are scattered nearly equally. Thus, clouds which have droplets of water with A is much greater than lambda are generally white. At sunset or sunrise, the sun's rays have to pass through a larger distance in the atmosphere. Most of the blue and other shorter wavelengths are removed by scattering. The least scattered light reaching our eyes, therefore the sun looks reddish. This explains the reddish appearance of the sun and full moon near the horizon. Optical instruments. A number of optical devices and instruments have been designed utilizing reflecting and refracting properties of mirrors, lenses and prisms. Periscope, kaleidoscope, binoculars, telescopes, microscopes are some examples of optical devices and instruments that are in common use. Our eye is one of the most important optical devices the nature has endowed us with. The microscope. A simple magnifier or microscope is a converging lens of small focal length. In order to use such a lens as a microscope, the lens is held near the object, one focal length away or less, and the eye is positioned close to the lens of the other side. The idea is to get an erect, magnified, and virtual image of the object at a distance so that it can be viewed comfortably, that is, at 25 cm or more. If the object is at a distance f, the image is at infinity. However, if the object is at a distance slightly less than the focal length of the lens, the image is virtual and closer than infinity. Although the closest comfortable distance for viewing the image is when it is at the near point distance d is approximately equal to 25 cm. It causes some strain on the eye. Therefore, the image formed at infinity is often considered most suitable for viewing by the relaxed eye. We show both cases. The linear magnification m for the image formed at the near point d by a simple microscope can be obtained by using the relation m is equal to v upon u is equal to v into 1 upon v minus 1 upon f is equal to 1 minus v upon f. Now, according to our sign convention, v is negative and is equal in magnitude to d. Thus, the magnification is m is equal to 1 plus d upon f, equation 39. Since d is about 25 cm, to have a magnification of 6, one needs a convex lens of focal length f is equal to 5 cm. M is equal to h dash upon h, where h is the size of the object and h dash the size of the image. This is also the ratio of the angle subtended by the image to that subtended by the object. If placed at d for comfortable viewing, note that this is not the angle actually subtended by the object at the eye, which is h upon u. What a single lens simple magnifier achieves is that it allows the object to be brought closer to the eye than D. We will now find the magnification when the image is at infinity. In this case, we will have to obtain the angular magnification. Suppose the object has a height h. The maximum angle it can subtend and be clearly visible without a lens is when it is at the near point, that is a distance d. The angle subtended is then given by tan theta 0 is equal to h upon d is approximately equal to theta 0. Equation 40. Find the angle subtended at the eye by the image when the object is at u. From the relations, h dash upon h is equal to m is equal to v upon u. The angle subtended by the image tan theta I is equal to h dash upon minus v is equal to h upon minus v into v upon u is equal to h upon minus u is approximately equal to theta. The angle subtended by the object when it is at u is equal to minus f. Theta I is equal to h upon f. Equation 41. As is clear from figure, the angular magnification is m is equal to theta I upon theta 0 is equal to d upon f. Equation 42. This is 1 less than the magnification when the image is at the near point. Equation 39. But the viewing is more comfortable and the difference in magnification is usually small. In subsequent discussions of optical instruments, that is microscope and telescope, we shall assume the image to be at infinity. A simple microscope has a limited maximum magnification which is less than or equal to 9 for realistic focal lengths. For much larger magnifications, one uses 2 lenses, one compounding the effect of the other. This is known as a compound microscope. A schematic diagram of a compound microscope is shown in figure. The lens nearest the object, called the objective, forms a real inverted magnified image of the object. This serves as the object for the second lens, the eyepiece, which functions essentially like a simple microscope or magnifier, produces the final image which is enlarged and virtual. The first inverted image is thus near, at or within the focal plane of the eyepiece, at a distance appropriate for final image formation at infinity, or a little closer for image formation at the near point. The final image is inverted with respect to the original object. We now obtain the magnification due to a compound microscope. The ray diagram of figure shows that the linear magnification due to the objective, namely h dash upon h, equals m0 is equal to h dash upon h is equal to L upon f0. Equation 43, where we have used the result tan beta is equal to h upon f0 is equal to h dash upon L. Here h dash is the size of the first image, the object size being h and f0 being the focal length of the objective. The first image is formed near the focal point of the eyepiece. The distance L, that is, the distance between the second focal point of the objective and the first focal point of the eyepiece, that is, focal length Fe, is called the tube length of the compound microscope. As the first inverted image is near the focal point of the eyepiece, we use the result from the discussion above for the simple microscope to obtain the angular magnification ME due to it. Equation 39, when the final image is formed at the near point, is ME is equal to 1 plus D upon FA. Equation 44a. When the final image is formed at infinity, the angular magnification due to the eyepiece Equation 42 is ME is equal to D upon FE. Equation 44b. Thus, the total magnification according to equation 33 when the image is formed at infinity is M is equal to M0 into ME is equal to L upon F0 into D upon FE. Equation 45. To achieve a large magnification of a small object, the objective and eyepiece should have small focal lengths. It is difficult to make the focal length much smaller than 1 cm. Also, large lenses are required to make L large. For example, with an objective with f0 is equal to 1.0 cm and an eyepiece with focal length fe is equal to 2.0 cm and a tube length of 20 cm, the magnification is m is equal to m0 into me is equal to L upon f0 into D upon fe is equal to 20 upon 1 into 25 upon 2 is equal to 250. Various other factors such as illumination of the object contribute to the quality and visibility of the image. In modern microscopes, multi-component lenses are used for both the objective and the eyepiece to improve image quality by minimizing various optical aberration, that is, defects in lenses. Telescope. The telescope is used to provide angular magnification of distant objects. It also has an objective and an eyepiece, but here the objective has a large focal length and a much larger aperture than the eyepiece. Light from a distant object enters the objective and a real image is formed in the tube at its second focal point. The eyepiece magnifies this image, producing a final inverted image. The magnifying power M is the ratio of the angle beta subtended at the eye by the final image to the angle alpha which the object subtends at the lens or the eye. Hence, M is approximately equal to beta upon alpha is approximately equal to H upon Fe into F0 upon H is approximately equal to F0 upon Fe. Equation 46. In this case, the length of the telescope tube is F0 plus Fe. Terrestrial telescopes have, in addition, a pair of inverting lenses to make the final image erect. Refracting telescopes can be used both for terrestrial and astronomical observations. For example, consider a telescope whose objective has a focal length of 100 cm and the eyepiece a focal length of 1 cm. The magnifying power of this telescope is M is equal to 100 upon 1 is equal to 100. Let us consider a pair of stars of actual separation 1 minute. The stars appear as through they are separated by an angle of 100 into 1 minute is equal to 100 minute is equal to 1.67 degree. The main consideration with an astronomical telescope are its light gathering power and its resolution or resolving power. The former clearly depends on the area of the objective. With larger diameters, fainter objects can be observed. The resolving power or the ability to observe two objects distinctly which are in very nearly the same direction also depends on the diameter of the objective. So, the desirable aim in optical telescope is to make them with objective of large diameter. The largest lens objective in use has a diameter of 40 each, which is similar to 1.02 meter. It is at the Yerkes Observatory in Wisconsin, USA. Such big lenses tend to be very heavy and therefore difficult to make and support by their edges. Further, It is rather difficult and expensive to make such large-sized lenses which form images that are free from any kind of chromatic aberration and distortions. For these reasons, modern telescopes use a concave mirror rather than a lens for the objective. Telescopes with mirror objectives are called reflecting telescopes. They have several advantages. First, there is no chromatic aberration in a mirror. Second, if a parabolic reflecting surface is chosen, spherical aberration is also removed. Mechanical support is much less of a problem since a mirror weighs much less than a lens of equivalent optical quality and can be supported over its entire back surface, not just over its rim. One obvious problem with a reflecting telescope is that the objective mirror focuses light inside the telescope tube. One must have an eyepiece and the observer right there, obstructing some light, which is depending on the size of the observer cage. This is what is done in the very large 200-inch, which is similar to 5.08 meter diameters, Mount Palomar Telescope, California. The viewer sits near the focal point of the mirror in a small cage. Another solution to the problem is to deflect the light being focused by another mirror. One such arrangement using a convex secondary mirror to focus the incident light, which now passes through a hole in the objective primary mirror, is shown in figure. This is known as a Cassegrain telescope after its inventor. It has the advantages of a large focal length in a short telescope. The largest telescope in India is in Kavalur, Tamil Nadu. It is a 2.34 meter diameter reflecting telescope, which is Cassegrain. It was ground, polished, set up, and is being used by the Indian Institute of Astrophysics, Bangalore. The largest reflecting telescopes in the world are the pair of Keck telescopes in Hawaii, USA, with a reflector of 10 meter in diameter.